Hello, everybody. Welcome to this second lecture on circulation models. Um, Obviously, this is the first of two that you're going to be getting directly through a YouTube link online, um, as I've got some stuff going on for the department, and then I have a trip down to California, Chicago, for the West Lakes AAG conference. So hopefully the quality is good enough. I'll just be kind of going through things at a pretty decent pace. So once you get to a slide, pause it, take your notes, then listen to me and add to your notes as you're going. So I think that'd probably be the best way to go through things. So we're going to go ahead and dive into this. Just another quick check-in with our snapshot of the week. Nothing's really changed. Keep reading through chapter 7 if you're following along in the book. Watch. We have nothing to watch this week. Make sure you're getting your post in for discussion 3. Here we can see our due dates coming up, your week 7 climate connection, your week 7 quiz, and your discussion 3 are all due on the exact same day at the exact same time. So make sure you're getting those in as you would normally do. Despite me being gone, those are still going to be the due dates just because we're getting the same lectures on the same days. And then your final project topic submission is going to be due, don't forget, on the 29th of October. That's a Friday, 11:59 p.m. So make sure you are getting all of that stuff in. Hold on, just a tick here. I might be. That's a Sunday. My bad. Not a Friday. So you have through that weekend to get it in for the final project topic. Slight typo on my part. I apologize. All right. So what are we going to focus on today? Well, last class on Monday we talked about kind of these two dominant patterns that we consider when looking at global circulation patterns, and not from a top-down perspective necessarily. If you recall, we were looking at things from a side view. So if you were to cut the Earth in half and you were looking at these big circulation patterns that were going on kind of on the edge of the planet, not necessarily straight down on it, that's what we were kind of looking at. We looked at Hadley's general circulation model, which was kind of our first attempt at it. Remember, he got a few things right, got a few things wrong. Air does, because of thermal buoyancy, rise at the equator and move poleward, but thanks to the rotation of our planet, which is what the two or three celled circulation model that we looked at towards the end of class shows us, is that when you have these circulating, or you have a rotating Earth, right, your patterns of wind are going to get deflected as you move poleward. So we get our northeast trade winds or southeast trade winds, depending on which hemisphere you're in. We get our mid-latitude westerlies, and we get our polar easterlies. So these dominant patterns really kind of set up really everything else, right? And this three-tiered circulation model that we talked about towards the end is driven by a lot of different stuff, not just thermal buoyancy and air cycling through. And that's what we're going to focus on today, is modifications to that generalized or idealized schema. So looking here at observed surface patterns. First off, we're going to start by looking at our global systems of pressure and wind, kind of a little bit of a recap, adding in all the new information that we know. So we're going to start in the low latitudes here, between the equator and 30 degrees north and south. This is just to kind of recap, and I would make your own little diagram in your notes just so you remember this stuff, likely for your quiz as you're going through. So we're looking at a side view of the troposphere in the low latitudes here. Obviously, based off of our radiation budgets, we've got incoming solar radiation centered mostly on the equator, right? Moving between 23.5 degrees north and south throughout the year. But the dominant bulk of that is going towards the equator. Now, if we were to look at our 500 millibar level, it'd be somewhere right around there. near the 30 degrees north and south, where your air is cooler and denser. Obviously, we have a different height there. And we talked about that right at the end of class on Monday, where you've kind of got this sloping gradient for pressure from the equator, where air is most expanded, to the poles where it's densest. So you get kind of this sloping surface that we see presented here. If we were to look up a little bit further, our 300 millibar level, it's a little bit more pronounced that far. We see a little bit stronger of a gradient as we go further up, decreasing in pressure further up in altitude. So right around that 300 millibar level, that's where we could assume, for example, that our high pressure system aloft is most focused. And we would have low pressure systems aloft over 30 degrees north and south. That high pressure aloft, we can think of kind of like this air rising and piling up and pushing off to either side, is going to make air move poleward. That low pressure at the surface is where air is going to be kind of working inwards. We'll get there in a second here. So this sets up the pattern, right? Highs on the surface at 30 degrees north and south, lows aloft at 30 degrees north and south, and then low at the equator, high aloft at the equator. Okay. So we've got this descending air, right, from 30 degrees north and south aloft, descending down. We've got air that is lost a chunk of its moisture. It's warming adiabatically instead of cooling. And we kind of talked about and hinted at this is where our most prominent deserts are, is right around that 30 degrees north and south range. Those are our subtropical high pressure systems. Then you move in. Those are the trade winds. They're deflected, obviously. We have our northeast and southeast trade winds. We saw how those were deflected by the Coriolis effect, converging at the equator. Talk about that in a minute. But these trade winds are driven by this equatorward flow. It's deflected by the Coriolis force. We mentioned they were named such because they were basically what enabled sailing ships to move goods between Europe and North America. I'm going to scoot my computer out just a little bit. There we go. In the northern hemisphere, they're blowing from the northeast, right? When we're talking about wind and we're referencing wind, we're talking about it in regards to the direction it's coming from. So a north wind is coming from the north, not blowing to the north. Same thing here, right? A northeast trade wind is coming from the northeast, and a southeast trade wind is coming from the southeast. They're converging near the equator in a region that's got a weak pressure gradient. This is called the doldrums or the intertropical convergence zone. In the doldrums, there are light winds and humid conditions that basically provide pretty monotonous weather. The intertropical convergence zone is just that low pressure system where the trade winds converge. We see it as basically a band of visible clouds throughout most of along the equatorial region. We saw it, and we'll see it again in one of the figures I showed on Monday. That air along the equator is warmed. Once it gets there, warm air expands. This Hadley cell circulation continues. So now at that point where you've got this air piling up aloft over 30 degrees north and south, that's what we typically call our subtropical jet stream. We'll talk about jet streams at the end of the lecture here today, but that's where our subtropical jet stream is located, is right around 300 millibars in pressure at about 30 degrees north and south on both sides. There we go. There's the last of my annotations there. Now, there are other patterns. Now, one of the things that we haven't really talked about um, are what we call trade wind inversions. And that's what you're seeing in this lower series of circulating arrows here. Now, trade wind inversion just refers to characteristic temperature inversion that's usually present in the trade wind streams over the eastern portions of our tropical oceans. What it basically leads to are these large scale subsiding flows uh, that kind of, what's the best way to put it? As it's flowing away, kind of converging and constituting these descending branches of the Hadley cells. So you've got a couple different circulating components within the Hadley cell that's leading to this descending or subsiding flow around 30 degrees north and south. And you can see there, those are our trade wind inversions. So if we were to look at this from a temperature sense, you would see kind of a flip-flop in temperature because of uh, stratification within your lower atmosphere. So the intertropical convergence zone and the trades are the next things that we're going to look at. The ITCZ is usually illustrated by a dynamic chain of thunderstorms in the tropics. We can see them right here, highlighting them a little bit for us. I was doing that with my computer trackpad, so bear with me. Now, as does a lot of other patterns across our world, this migrates latitudinally with season. It does not migrate, it's suppressed over places affected by cold ocean currents. So if we think of these big atmosphere, these big oceanic gyres that we talked about, the western side of the basin, typically warmer waters, the eastern side, typically cooler waters. And that's what we see here is over the cooler waters, typically on the eastern side of your basins, this ITCZ is a bit suppressed, where over the eastern or the western portions, the warmer portions, it moves and it migrates because there's more moisture, there's more evaporation, there's more energy within the system. And because this ITCZ migrates, the trade winds also migrate seasonally. So they shift up and down latitudinally as well. Now we're going to look at some of our semi-permanent systems. So the first off, kind of discussing, and we've talked about them previously, but these big subtropical anticyclones, these high pressure cells, semi-permanent high pressure cells. Our generalized model has a belt of high pressure at 30 degrees north and 30 degrees south, right? About here and about here. And hey, look, these regions devoid of moisture, which is what this is looking at here, follow along pretty well with that model. Now, in reality, this isn't continuous over the surface of our planet. What starts to trip up these generalized circulation models is land, both in subtropical anticyclones that we're talking about now and some of the stuff we're going to be talking about later, because there's so many other things in the way and there's so much of a temperature differential and therefore a pressure differential when you're over land versus over the ocean. Over the ocean, flat surface, relatively spread out insulation that starts to follow a latitudinal trend. But over land, that all goes away because you have so many other things, mountains, bigger bodies of water in mid-continental regions like the Great Lakes, etc. So in reality, these only happen in their generalized sense over the oceans. Um, During the summer, they're a lot stronger because of relatively cool conditions over oceans. So you again get that kind of stratification within your lower atmosphere, which can lead to uh, differences in how air is moving about the troposphere. And heating of land kind of tends to offset that sinking air. So we don't really get these big dominant high pressure systems that set up over land the same way they set up over water. Here's what they typically look like in, well, January across the world. There are some that set up over land, these high pressure systems. The Canadian high, for example, or the Siberian high, both. But we'll talk about those in later lectures. But others, the Pacific high, for example, or the Bermuda high, the South Pacific high, which is off the western coast of South America, all of these we see setting up predominantly over ocean basins, as we would expect. Um, if we were to look higher up in the atmosphere, right around that 500 millibar level, if we're looking at streamlines and isotherms, uh, they would look something like this. We would see, predominantly speaking, high pressure systems right over the equator, which is where we expect them, right? We have air rising, piling up in the upper atmosphere. It's exactly what we see. Low pressure systems around the Arctic Circle, a little north of that. So kind of transitioning, those would be our polar lows before we get to the Arctic and the Antarctic, where we would have our polar highs. Um, we're seeing that kind of expressed here. Here's our semi-permanent pressure systems in July. Notice there's been a lot of shifting that's happened. In the southern hemisphere, right, we're seeing a much more consistent band around 30. It's their winter versus our summer. Um, you can see there is a thermal low that sets up over California, Pacific Northwest. That Pacific high has been pushed a little bit off coast, whereas in the Atlantic, the Mid-Atlantic basin, we see that Bermuda high expanded, being a little bit more prevalent. And again, here we see that those high pressure systems have pushed a little bit northward in July compared to where they were in January. All right, next looking at our global system of pressure and wind in the mid and high latitudes. Uh, in When we look at our high pressure systems, uh, we know that a lack of insulation in winter leads to low level stability within our atmosphere, stratification within our atmosphere. That frigid, dense air sinks and is starting to move back towards the equator. That creates our polar highs, which strengthen and maximum strength in the winter. What this leads to, or one of the things this leads to, is intensification uh, that forces our polar cells towards the equator. So what we typically see, and we'll see this in a slide coming up, is suppression of that polar high or the polar jet stream, the polar vortex during the summer months, and then expansion and intensification of it during the winter months. Uh, the polar vortex, I always love that because it really became a prominent term when I was first learning meteorology, at least sensationalized in the way the media does. But that polar vortex, this cyclonic system or anticyclonic system, the polar high, polar jet stream, pushes south. As it pushes south, you get this, a lot of times, this trough and ridge system, what we call the Rossby waves. We'll talk about those later, where if it kind of entrenches, it kind of gets stuck in place there for a little bit. It can do that. You get this very cold air coming from the Arctic. That's when in February, and it's 30 degrees below, well, that's what's driving it. Our low pressure systems within our polar cells are confined to our ocean basins, much like the polar highs are. Their existence is also tied to surface temperature variations between land and water, as you would expect. But warmer oceans are promoting this low level atmospheric instability, air rising off of the warmer surface of our ocean versus the surface of the air, or well, the temperature of the lower air. Um, and these lows are typically located where cold surface air from our polar high meets poleward moving air from subtropical anticyclones. And you get this low pressure system uh, at the surface. So what does this mean? What is, as far as relationships go? So the convergence between these polar and subtropical streams is termed the polar front. What you typically see uh, along this band of latitudes is cyclogenesis. So the rotation and imparted rotation leading to mid-latitude cyclones. Um, because of the steep thermal gradient going from south of the polar front to north of the polar front, if we're using the northern hemisphere, for example, that steep polar gradient allows and really supports the development of cyclogenesis, or supports cyclogenesis, the development of these mid-latitude cyclones. And that's what really brings most of the weather that we experience during the colder months. We just got hit with a mid-latitude cyclone. That's what brought all that rain last weekend, was this mid-latitude system. A couple weeks down the road, a month down the road, that would have been a lot of snow. But because we had warm enough temperatures, we experienced it as a bunch of rain. And as everything does, depending on the season and the thermal differences, these regions expand and shrink depending on the time of year. So we're going to look at, kind of like we did with along the equator. Um, this is a side view of the troposphere in the mid and high latitudes. There we go. There is 30 degrees north, 90 degrees north. There's the position of our subtropical high and our subtropical jet stream. We've got subsiding air there, moving equatorward. And because it's a high at the surface, not high aloft, air is moving poleward as well, moving out and away from the subtropical high at 30 degrees north and south. So the circulation in the polar cell is driven by subsidence near the poles that produces surface flow that moves equatorward, and vice versa. We've got stuff coming up from the mid latitudes as well. So those would be our westerlies. Here's our pressure gradient, or our temperature gradient, pardon me. That would be our polar front. So we've got a steep pressure gradient there, and we'll see that illustrated here in a second. So notice already those are much, much lower. So as we go, there's our polar high. So we've got two high pressure systems, right? Our subtropical high and our polar high, both pushing air towards the mid latitudes. Those are our polar easterlies versus our mid latitude westerlies. We've got descending air there from a low pressure system aloft. And you can see there, that's what we're talking about when we're saying there's a steep gradient. So this gradient here is what gives rise to this dominant cyclogenesis, driving most of the weather patterns, or many of the weather patterns that we're seeing strike us, these big systems strike us throughout our colder months. So if we're looking in terms of gradient, you can see the larger the arrow, the stronger the gradient, right? That polar front is also where what we term as the polar jet stream. At the surface, we have a subpolar low, air rushing in to fill that low pressure void from the high pressure systems on either side of it. All right, now our jet stream. So jet streams are these relatively narrow bands of strong wind in the upper levels of our atmosphere. We can see two examples of them here, just two little diagram schematics. The winds blow from, pardon me, west to east in the jet streams, but flow often shifts north and south depending on what's driving it at a given time of the year. Jet streams are following these boundaries between hot and cold air. Since these hot and cold air boundaries are most pronounced in the winter, jet streams are stronger for both the northern and southern hemisphere winters. They intensify as the season gets colder, and that gradient gets stronger. The actual appearance of jet streams result from this complex interaction of a lot of different variables, right? These high and low pressure systems, warm and cold air, and seasonal changes. They meander across the globe, dipping and rising in altitude and latitude. Sometimes they split, they form eddies, they can even disappear altogether sometimes. Um, but more or less, they follow the sun. And that the sun's elevation increases each day in the spring, the average latitude of the jet stream shifts poleward. By summer, in the northern hemisphere, it's typically found near the US-Canadian borders. As autumn approaches, the sun's elevation decreases, the jet stream average latitude moves towards the equator. Here we can see just one example of that, right? We see kind of an eddying system here. We're looking at the 500 millibar level. So we've got, let's see if I can draw this out. We've got obviously our part of our jet stream here coming into the coast of Alaska down into the west coast of the United States and Canada here. We can see a jet stream kind of meandering its way back up through. And we see it splits, right? It goes down here. We've got this little eddying system here and a high pressure system here. So we can have a lot going on within our jet. So if we're looking at surface pressure patterns and impacts, our summer hemisphere, so whichever hemisphere it's summer in, sees weakening and contraction of those polar high and subpolar lows, and expansion of the subtropical highs. The ITCZ pushes poleward through tropical part of the southern hemisphere and contributes pretty heavily to tropical precipitation regimes. Flip-flop that for the winter hemisphere. Changes in that semi-permanent circulation cell trigger precipitation in the mid-latitudes. You get stronger thermal gradient, a lot more activity. And precipitation changes define the lower latitudes because thermal differences really are minimal. So wherever you're getting the most precipitation, that's kind of defining what is going on in the lower latitudes, really what time of year it is, where those dominant bands are from the intertropical convergence zone, because your thermal differences really aren't changing that much. So obviously I'm not stopping, I'm not pandering at all, so these are going to be a little bit shorter. So that's where I'm going to stop for this one. We will pick up next lecture on Friday, obviously going into this a little bit more deeply. So Thank you all. Hope you have a great day, and we'll see you again on Friday.